Hey guys, welcome to section 2. So in this video, we are going to talk more about the Stern-Gerlach experiment, which we saw in the last video. But now we are going to figure out how to construct a theory around how we can interpret these results and actually make some mathematical sense out of them. So what I have here is I have set up some axes. I've got the color axes in red and the hardness axes in blue. And so in the color axes we have white and black, and the hardness we've got hard and soft. And so what we've got here is then also we have some unit vectors, right, which are vectors with a magnitude of 1 along these axes, and hopefully you're familiar with how vectors work. If not, definitely see the description for my video on vectors. Okay, so now we can put another vector on this diagram that I'm going to call psi, and probably not the best, because I would like it to be a unit vector as well. So I'm going to call this psi, but I'll put the vector arrow over it. And that's a Greek letter. So psi vector can be expressed, in fact, in terms of the black and white unit vectors, as well as being expressed in terms of the hard and soft unit vectors. Right? If we do this, we can hopefully again from how vectors work using unit vectors and perpendicular axes, right? That's another thing too. These axes are perpendicular. We can write this psi as some constant a, or some scalar a, times the white unit vector plus b times the black unit vector. Again, hopefully you realize hats represent unit vectors. Then psi is also going to be a unit vector, but right now for full generality, any vector can be written in this way. Or it can also be written in terms of the other basis, in the hardness basis, right? Doesn't matter what the orientation of the unit vectors are, you can always do this, as long as you've got unit vectors that are not in the same direction, particularly in perpendicular directions. So we could also write this as c times the soft unit vector plus d times the hard unit vector. Okay, and part of how we can show that these are actually equivalent definitions is it turns out we can write the white and black unit vectors in terms of the soft and hard unit vectors and vice versa. And so hopefully you can see sort of geometrically how this might work. So let's write in orange. We know that the white unit vector, not that color, let's go orange here. We know that the white unit vector is the it would be the hard unit vector, the soft unit vector minus the hard unit vector over the square root of 2. Right? Hopefully you can see that we've got the component of the white unit vector is in the positive direction of the positive soft direction and the negative hard direction, right? And it would be sort of equivalent parts of both. You can sort of do the trigonometry with this if you're comfortable with vectors, and the root 2 is there because this still has to be a unit vector. And in fact, if you take the magnitude of this, you will find that it is a unit vector if you have that square root of 2 there. Similarly, the black unit vector is equal to the soft unit vector plus the hard unit vector over the square root of 2. Again, you should be able to see this geometrically. Now, we can write the other way, which is writing the hard and soft unit vectors in terms of the black and white unit vectors. So the soft unit vector is equal to the black unit vector plus the white unit vector. Right, this would really be the easiest one to see. The soft unit vector is made up of the black unit vector plus the white unit vector in equal amounts, right? And then you need the root 2 to make sure it has a magnitude of 1. And then the hard unit vector would then be the black unit vector minus the white unit vector over root 2. And you can see that these relations are equivalent, so you could use algebra to rearrange one of them and to rearrange like this set of equations and get this set, or the other way. So they're consistent. Okay. So the next thing I want to do is I've been hopefully using some familiar notation with you guys. Well, actually, first, just to point out that using these equations, you can show that some, A times the white unit vector plus B times the black unit vector can also be written as C times the soft unit vector plus D times the hard unit vector. And then you can actually find, if this is a nice exercise you may want to do on your own, is finding a relationship between A and B and C and D. Okay, so now I've been using hopefully some familiar notation with you guys right first. So now I would like to change it up a little bit so we get more into the quantum mechanics notation. So the first thing we're going to do is replace the hat on unit vectors with a different symbol. And we'll be talking about this symbol and be using this symbol throughout this entire course. And what it really represents, at least for right now, and really even through the course, but we'll find out a few more things that it also represents. But right now, what it represents is it represents a unit vector, and the notation that we'll be using looks like this. So this would be the hard unit vector. Okay, it's got a little, line, and then a triangular bracket, and then you put the label in there. So similarly, the soft unit vector would be written this way. Now if we go to a different color, the white unit vector would be like this, and the black unit vector be there. And then we can also, assuming this psi right now, and we'll see why this will be, is a unit vector, we can also write it like this. Okay, so now we're going to actually rename some of this stuff. So I'm going to erase this and rewrite it in the way that we'll be writing it in quantum mechanics. So here, the vector psi can be expressed as some constant CW, or it's a scalar, right? It doesn't necessarily have to be constant, but it's a scalar, CW, times the W unit vector, the white unit vector, plus CB times the black unit vector, I think it's not letting me write there, CB okay, and then this could also be equal. You can write it in the what we'll call the hardness basis, right? A basis is just a set of unit vectors that are perpendicular. A basis is a set of unit vectors, and so we wrote it here in the color basis. Now we'll write it in the hardness basis, where we have some CS times the soft unit vector plus some CH, the hard unit vector. Okay, and similarly we can still write these expressions, but instead of hats, we'll be using our new notation. I'm not going to write it all down. Hopefully you have this written down. You may want to write it down with our new notation, but I'm actually going to erase this for right now. But again, hopefully that makes sense, and we'll come back to this a little bit later. Okay. So now that I've shown this diagram that, may have no meaning right now to you guys, let's talk about what it means. What is the significance of doing this, and how will this give us our Stern-Gerlach experiment results? And so what we need to talk about now is probabilities. Right, so psi, this is going to be the vector that represents the state of a particle. So our electron, when we send it through the Stern-Gerlach apparatus, we can have it in the state psi. And these coefficients mean something very important. And what that means, and I will explain soon why we want it to be like this, and how we actually know that this is the expression for probability. So the probability of the particle being white is CW squared. Okay? Similarly, the probability of the particle being black is CB squared. Probability of being soft would be the C soft squared, CS squared. Probability of being hard would be CH. CH squared. Okay. And so, why is it squared? Right, that may be the first question you think of here. And so, right now I'm going to give a little bit of an argument of why we know that these probabilities have to be the square of the coefficients and not just the coefficients themselves. Or maybe you could say, well, why isn't it the cube or to the fourth power of the coefficient? So I'll explain that now. And so we know that the magnitude of psi, right? There's any vector. Psi is just, right now, we don't even need it to be a unit vector right now, but we'll see in a minute why it is. Any vector psi, the length of it has to be the same, whether I express it in the color basis or the hardness basis, right? We saw that these definitions are equivalent, so the length of psi has to be the same either way. But we know if we have perpendicular unit vectors, we know what the length of the vector is. It's just the square root of the sum of the squares of the components, right? Or we can also say that we know that the length squared, the magnitude squared of psi, that will just be a little bit easier to work with. So we know the magnitude squared of psi, that's psi, we know its magnitude squared has to be the same, right, in either basis. Well, in the color basis, it is CW squared plus CB squared. And this is why I'm doing the magnitude squared, just because then we don't need to have any square roots, right? But the magnitude squared, the length has to be the same, the length squared has to be the same in the hardness basis. So this would be the same as C hard, or C soft squared plus C hard squared. Right? This is just the length squared of a vector psi. But we also know something else. We know that probabilities have to add up to be the same amount. So we know that the probability that the particle is white plus the probability that the particle is black, we know that that has to equal 1, right? But this is the same, right? Because the particle can either be white or black, right? It's if you measure it, if you measure the color, even though we know it's in a state of being kind of both white and black at the same time, in a weird way. We know that really it's really, you know, if we measure the particle, once we measure the particle, it will either pick it's white or it's black. So the probability upon measurement is going to be 1 when we add the two up, because it's one or the other once we measure it. And this has to be equal to the probability of it being soft plus the probability of it being hard. In particular, these probabilities have to add up to be 1. Now, the only way that both of these equations can be true is if the probability is proportional to the square. Now, we could theoretically, if you wanted to, say that the probability is 2 times the coefficient squared, but then it would just be unnecessary complications in there. We know it has to be proportional, so we can actually, it's kind of arbitrary, but to be easier, we say that the probabilities are equal, right? And then we can show, if given that psi, because these probabilities have to add up to 1. So the magnitude of psi, or the magnitude squared of psi, is 1. These equations, right, not even counting this equals 1 part, the equation where the length has to be squared the same in either basis and the probabilities have to all add up to 1, those are inconsistent. Those would those at least are not fully consistent. You could not guarantee both of them to be true if you define the probability any other way than being just the coefficient, or any way than being the coefficient squared. So like not being just the coefficient or the coefficient cubed or the fourth power, or however you would want to define it. And then if we, of course, if we then defined the probability to be 2 times the coefficient squared, that would just mean the magnitude of psi would be 1 over the square root of 2, right? Or the magnitude squared would be 1/2, which you can show that yourself if you want to, but it's a lot easier to just say that psi is a unit vector, magnitude of 1, and so the probability is equal to the square of the coefficient. Okay, and so, yeah, so again, remember, it's important to know that the probabilities have to all add to 1. And this is, in fact, called normalization. And normalization is that the magnitude of psi is 1. So I'll write that because we are going to be using normalization throughout this entire course. So normalization is that the magnitude of psi equals 1. Although it's often written as the magnitude of psi, just because it's a lot easier to deal with magnitude squared, because then there's no square roots, so a lot of the times normalization is written this way. That is a very important thing in the statement of normalization. This is mathematical, but the statement is just probabilities have to add up to 1, which is a statement that hopefully we can all agree on. Okay, so now I've shown you this this setup of how we can do this. So now I want to go to our Stern-Gerlach experiment and show how this setup with these probabilities actually gives us the result of this experiment, and then we'll go from there. So the first thing is the electrons are in some random state, and it turns out if you put them through the Stern-Gerlach experiment in just any random state, it will be half and half. But now what we're doing is we take the white ones, all the white electrons, we put in a color box, we get out the white ones, and we take them. And so the state of the particle is here. This would be this new state of the particle once we measure it. Hopefully you can see I'm doing this in this pink color. Okay, now so once we've measured it, we found out that it has to be in this state. Now if we measure the color again, right, well, we've found out that all the particles are in this state of being white. So if we measure the color again, well, the probability of being white is 1, right? Because the state would be, right, if we write out what our state would be, the state of the electron, I can write it like this, once we measure it, would literally just be the white unit vector. So the coefficient squared would be 1. Okay, so now let's go to our next example, our next case of the Stern-Gerlach experiment. Actually, sorry, I'm gonna undo a few things because I want to get the... Okay, so now we measure the particle to be in this this state to be white, right? So we take all the white particles. So the state now, psi, or sorry, the state of the electron, I think I wrote it, was state of the electron is white. Okay, so now we measure that. But if we take the white unit vector, right, we know that the white unit vector we showed before is equal to, let's see, it's soft unit vector over the square root of 2. I'm just going to break this up, minus the hard unit vector over the square root of 2. Right, which means, so we measure we measure the electron. The electron is in the state of definitely being white, and then if it's in the state of being white, the probability if you're in the state of being soft is 1 over root 2 squared, right, which is 1/2. And similarly, the probability of being hard is negative 1 over root 2, right? That's the coefficient for being hard. That's a CH squared, which is 1/2. And again, these add up to 1. So, if you're in the state of definitely being white, then your probability of being soft is 1/2 and probability of being hard is 1/2, which is exactly what the Stern-Gerlach experiment says. So now the electrons were in this state, but then we measured them for their hardness. And now we know what state they're in. Well, now we're taking all the soft electrons and putting them here. Right, so we're taking the soft electrons now. So there was a 50-50 chance of being hard or soft, but now we're taking the soft ones, and now we know the soft ones are in this state, of being the soft unit vector. So now, after this step, we know that the state of the electron is the soft unit vector. Okay, but now we want to measure the color again. And if you take the soft unit vector, we know that the soft unit vector is the black unit vector, right, black unit vector over root 2 plus the white unit vector over root 2. And then we know that the coefficient for being black is 1 over root 2, coefficient for being white is 1 over root 2. So the probability, okay, I have to erase this here, so the probability of being black would be 1 over root 2 squared, which is 1/2. And similarly, the probability of being white is 1 over root 2 squared, which is 1/2. Right? So now hopefully we can see that, sorry, this is equals, okay. So hopefully we can see why this will happen, right? Because the particle was in the state of being white, but then we measured it for its hardness, and then we found out, well, the ones we took were in the state of being soft. And now that we know they're in this state, we no longer know the color. Hopefully that makes sense. You may have to sort of repeat that in your mind or watch this part a few times, but hopefully that would make sense. That once we measure the hardness, and it's here, we no longer know the color. Okay, so now in our last example, we have again take all the white electrons, and then we put them through a hardness box. We have 50% hard, 50% soft, and right, which is what we had gotten before. Makes perfect sense. Yeah, so they're in this state of being white. This is the state of the electrons, and then we measure it, and we find out that 50% of them are soft, and 50% of them are hard, and we measure them, and they're in this state, right here. So we have 50% of them are in this state, and then 50% of them are in this state. But then we recombine those beams, which is just like adding these two vectors, and when we add these two vectors, what do we get? Well, we get the white unit vector again. So when we combine those two states, add those vectors, we get the white unit vector back. And so these particles will be in the state of they'll be in the state of being the soft, right? This is 1 over root 2, really. And here this is going to be negative hard, just because of how it is on the diagram, right? It's in the white, and we break it up into these two states when we measure it, but then when we put them back together, they're back into this state of being with the white unit vector. So hopefully this makes sense. Now I'm going to talk about one more word here, and this will be the last part of this video, which is a superposition. And what a superposition is it is being sort of in the combination of these two states. So, for example, this, right, we're writing psi is these coefficients. This is a superposition. This is writing psi as a superposition of being white and being black. This is writing psi as being a superposition of being soft and hard. And what this superposition means, essentially, is we are, it has a probability of being one, a probability of being the other. But before we measure it, right, if we take, for example, this state psi, here, let's make this psi. Before we measure psi, can you tell me if it's white or black? No, in fact, you cannot, because it's not either. It's somewhere in between. But so it's not both, right? It can't be both, and it can't be. But it's like it's one or the other. Once we measure it, it's one or the other, but it can't be both, right? That it's not both, it's not neither, it's not one, it's not the other. It's in a superposition. That's what a superposition is. You know, if we have a particle that's definitely soft, it's not black, it's not white, it's not both, but it's not neither, right? It's going to be one or the other once we measure it, but before we measure it, it's not both, it's not either, and it's not neither, which is one of the weirdest things quantum mechanics does. But you can see on the diagram that if this is how reality works, which it turns out it is, as you see on the diagram, that the superposition, it's really just inherently its own thing. It's again, it's not both. You can't be both at the same time. It's just got a probability of being one, probability of being the other, but until you measure it, it's not one or the other, but it can't be both and it can't be neither. So that's what a superposition is. Okay, so hopefully this makes sense, and I will see you in the next video.